Hi, today we are going to start looking at differentiability. So we're looking at whether functions are differentiable. So if our function f is continuous at x equals a, and our left-hand derivative at x equals a is equal to right-hand derivative at x equals a, or in other words, our limit of f prime at x as x approaches a from the negative side equals our limit of f prime x as x approaches a from a positive side. If it meets that criteria, then we can say our function f of x is differentiable at x equals a. Now, for it to be differentiable at x equals a, it means that it must be continuous at x equals a, and our left-hand tangent slope must equal our right-hand tangent slope. So we're going to start by looking at some functions that are not differentiable and the specific reasons why they are not. So this first one, we can tell by looking at it's not differentiable because this is not continuous. We can see that our graph jumps from this point to this point. On this graph, no scale is written, but essentially we would have to approaching -2 from the left, this should equal -1, and approaching -2 from the right, it should equal +1. So we can see it's discontinuous. So we can say f is discontinuous at x equals -2. Therefore, f is not differentiable at x equals 0. Okay, another type of situation where you have something that's not differentiable is known as a corner. So these often occur when we have, for example, absolute value functions. So if we have f of x equals absolute value of x plus 2, we end up with something that looks like this. Now, from looking at this, we can see it's continuous, but we can see that our left-hand slope does not equal our right-hand slope, but we'll also prove that mathematically. So what we can say is our limit or, our slope, which is f prime x, is equal to our limit as h goes to 0. Now in this case, we're looking at this location here. So that would be f of -2 plus h minus f of -2 over h. So we're going to simplify this a bit. So our limit as h goes to 0 of, if we substitute this into this equation, we'd have the absolute value of -2 plus h plus 2. So 2's are going to cancel out. So that's going to just be the absolute value of h. And then minus f of -2. If I substitute -2 in, that gives me absolute value of 0, which is just 0. So we can see that our limit, as we approach 0 for h value, is equal to absolute value of h over h. Now we have to break this into left-hand or right-hand limits. So if we look at our limit as h approaches 0 from the negative side, that would make our absolute value of h -h over h. Now we can see that that would simplify to -1. Where if we have our limit, so if we look at our limit as h approaches 0 from the positive side or right side, we know that the absolute value of h becomes positive h over h, which is 1. So what we can see is these two slopes give us different values. So therefore, they are different as we approach from the left side versus the right side. So we can say our limit of f of x as x approaches our value of -2 from the negative side does not equal our limit of f of x as x approaches -2 from the positive side. Therefore, f is not differentiable. So we end up with a corner when these limits do not equal each other. And we should include not just not differentiable, but not differentiable at x equals -2, because technically it would still be differentiable in other parts of our graph, but not at that particular location. Okay, so next we have something known as a cusp. So we can see that we have something continuous. However, it looks like the slope as we're going towards 0 does not match our slope going towards 0 from the other side. So we're going to show that mathematically and show that it's discontinuous. So we're going to be looking for essentially our slope at an x value of 0. So that's the same as our limit as x approach, or sorry, as h approaches 0. Of f of 0 plus h minus f of 0 over h. So we'll start putting our equation into this. So if I have 0 plus h going in for my x here, 0 plus h is just h. So that's going to give me h squared inside a cube root. And then we've got the plus 1. And then we're going to have minus f of 0. If I put 0 in here, 0 squared is 0, cube root of 0 is 0, plus 1 gives me 1. So we've got plus 1 minus 1 over h. Because we had plus 1 minus 1, those terms are essentially going to cancel out. Now to help continue solving this, I will change this into exponential form. So that's h to the power of 2 over 3 over h. So that's our limit as h goes to 0 of h to the, if you remember your exponent laws, if you're dividing, you're subtracting this exponent. This is technically to the power 1, so 2/3 minus 1 would be -1/3. So we've got h to the power of -1/3. We can rewrite that as our limit as h goes to 0 of 1 over the cube root of h. So now we'll look at approaching this from both sides. So if we look at our limit, as h approaches 0 from the negative side of 1 over the cube root of h, we're going to get to a very, very small number. But because we're approaching from the negative side and it is a cube root, we're going to have a negative value down here. So 1 divided by something that's negative and very small is going to give us negative infinity. Now, if we look at our limit, as h goes to 0 from the positive side of 1 over the cube root of h, it's going to be the same idea. We're going to get something very, very small, but because we're approaching from a positive side, we're only going to have positive numbers in here, so it's going to approach positive infinity. So when we have one side approaching negative infinity and the other side approaching positive infinity, it doesn't matter in which order those occur, we end up with a cusp. And for this, we can once again say we can say that our limit as h goes to 0 from the negative side of f prime x does not equal our limit as h goes to 0 from the positive side of f prime x Therefore, f of x is not differentiable at x equals 0. Okay, last of these ones that we're going to look at is what's known as a vertical tangent. So this is an example of it. So we've got f of x as a cube root of x plus 2. So we see we've got this graph here. It's continuous, but it technically has a vertical tangent for its slope in one spot. So we will go over showing mathematically why it doesn't exist or it's not differentiable. So what we're going to be looking at is our limit as we approach this -2. So we're looking for f prime of -2, which is our limit as h goes to 0 of f of -2 plus h minus f of h over h. So this is our limit as h goes to 0 of, if we substitute this into here, -2 plus h plus 2 would just be h. So the cube root of h minus f of h. So if I substitute, actually, sorry, because it shouldn't have been f of h, it should be f of our a value, which in this case, our a value was -2. So if we substitute -2 in here, -2 plus 2 is 0, cube root of 0 is 0, and that's being divided by h. So to simplify this down a bit, this is limit as h goes to 0 of h to 1 over 3 over h. So it's our limit as h goes to 0 of h to the negative 2/3. So that's our limit as h goes to 0 of 1 over a cube root of h squared. Okay, so we'll look at approaching 0 from both sides. So we've got our limit as h goes to 0 from the negative side of 1 over the cube root of h squared. If we're approaching 0 from the negative side, we're going to have a negative value that's very small. But when we square it, it's going to make it positive so that when we take the cube root, we also get positive. So we have 1 divided by something very, very small. So that's going to give us positive infinity. And then over here, we've got our limit as h goes to 0 from the positive side. And if we square something positive, it'll be positive. Taking the cube root gives us something positive. And it's going to be infinitely small. So 1 divided by something positive and infinitely small also gives us infinity. Now, because even though these are the same values, because infinity is not a specific value, we can say this is not differentiable. And it's referred to as a vertical tangent because if we drew a tangent line through this point here, you would notice that at -2, our tangent line would be purely vertical. Okay, when given a graph and asked to state why points are not differentiable, we'll give one of 3 main reasons. One is it's discontinuous. 2, left-hand derivative does not equal right-hand derivative. So in other words, our slopes on the left side does not equal our slope on the right side, or it is a vertical tangent. So we'll look at an example. So if we have this graph here, we only determine at which points a function below is differentiable. If a point is not differentiable, state the reason. And essentially, we have all the points we want to talk about marked out. So we've got A lines up with this point, B with these points, C with this point, D with this point, E would be here, F will be here, G will be here, H is here, I is here, and J is here. So first thing we want to do is mark our differentiable points. And we might cross these out as we go looking through them. That way we don't have to worry about them as we look at other stuff. So we can see A, although it's continuous, this slope does not meet this slope, so therefore not differentiable. B, we have a jump going on here, so that's not continuous. That's a point of discontinuity. But C, we can see that it's continuous and this slope equals this slope. So we can say C is differentiable. Now it looks like we have the same thing with D here. It's continuous. Both sides look like they have the same slope. So D is also differentiable. As we approach E, we can see that it's not continuous. Our graph here jumps from here to here. So it's discontinuous there. F, we can see it's continuous, but this slope does not equal this slope. G, discontinuous. We're missing a point here. H, we can see that it is continuous. This slope looks like it equals this slope. Up here, continuous but different slopes. Down here, continuous but different slopes. So it's differentiable at C, D, and H. Okay, so next we'll go through mark all of our discontinuous points. So we can see that jumps from here to here at B, so we know that's discontinuous there. Here we're jumping from here to here, so it's discontinuous at E. G, it also is discontinuous because we have this hole. And then we're going to look for ones where our left-hand derivative does not equal our right-hand derivative, or in other words, our slopes are not equal. So that would be A, F, I, and J. So in this case, we didn't have a vertical tangent. Okay, so next we're going to talk about existence of a limit, continuity, and differentiability. So these three are related, but only in one direction. If something is differentiable, it is automatically continuous. So if something is differentiable, it is continuous. Because part of our definition of differentiability is it is continuous. Now, it doesn't go the other way because continuity doesn't guarantee that our left-hand slope equals our right-hand slope. Now, we can also say that if something is continuous, it has to have existence of a limit because part of our definition of continuity is that there is this limit. Now, our existence of a limit doesn't state that our function has to exist at that location, which is why existence of a limit does not imply continuity. So we're going to look at this graph and determine which statements are true. So first one is our limit of f of x as x approaches -6 exists. So we can see as we approach -6 from the negative side, we're down at -2. While as we approach it from a positive side, we're at +2. So we can say that this one's false. And we can say it's because our left-hand limit does not equal our right-hand limit. Now next we've got our limit as we're approaching 1 from the negative side equals our limit of f of x as we approach 1 from the positive side. So as we approach from the negative side, it's 2. As we approach from the positive side, it's also 2. So we can say this one's true. And we saw from our graph our left-hand limit did equal our right-hand limit. Now this one, we've got our limit of f of x equals f of 1, but we can see our limit at f of x as x approaches 1 was 2. Well, f of 1 was way down here at -4. So we can say this one's false. And we know it's false because it's discontinuous at x equals 1. Next, we've got as we approach 1 from the negative side, our slope is equal to our limit as we approach 1 from the positive side of f prime x. Now we can see our slope on this side as we're approaching it is 0. This is a non-zero slope on this side, so we can say false. We can say our left-hand derivative does not equal our right-hand derivative. Next, we're going to be looking at as we approach 4, the positive and negative side. So as we approach 4, 1, 2, 3. As we approach here, saying is our derivative the same as we approach from both sides? In fact, it is. So we can say it's true, and we know this because the graph is smooth. Which means, therefore, left-hand derivative equals right-hand derivative. Okay, so this next one, it's saying our limit as we're approaching 4 of f of x minus f of 4 over x minus 4. So it's looking for our slope at 4 and saying it's less than 0. But we can see from here at 4, we have a positive slope, which means our limit is going to be greater than 0. So we can say false. F has a positive tangent slope at x equals 4. Therefore, f prime of 4 is greater than 0. It's not less than 0.